Today we're going to do some math for fun, which is often the case. Since the beginning of time, mankind has sought the answer to one and only one question. What would happen if we combine the Gaussian and the Bernoulli integrals? Today I attempt to answer that question. Does this thing even have a closed form? We'll find out later. So we're interested in the integral from 0 to infinity of x to the minus x times e to the minus x squared. And one would think we could get away with applying a similar line of thought as we did with the Bernoulli integral, that is x to the minus x. This can be expanded as e to the minus x log x. And this thing has a really nice series expansion because, of course, it is an exponential function. So we know e to the z equals the sum over k from 0 to infinity of z to the k over k factorial for all complex numbers z. So e to the minus x log x would be the sum over k of negative 1 to the k times x to the k log to the k of x over k factorial. So subbing this into my target integral I yields the integral from 0 to infinity of e to the minus x squared times the sum over k of negative 1 to the k x to the k log to the k of x over k factorial dx. This thing being independent of the index variable k can be taken inside. So we have the integral from 0 to infinity of the sum over k of negative 1 to the k times x to the k e to the minus x squared log to the k of x over k factorial, terribly sorry about that, dx. We'll now switch up the order of the integration and summation operators, and while I'm at it, I'm going to take all of the k terms, that is to say the terms independent of x outside the integration operator. So we have negative 1 to the k over k factorial times the integral from 0 to infinity of x to the k e to the minus x squared log to the k of x dx. So now let's try evaluating this integral here that I'm going to call I sub k. Okay, cool. So this looks like it could be related to the gamma function. So first let me define I of k as the integral from 0 to infinity of x to the k times e to the minus x squared dx. And the reason I want to do that is because if I differentiate with respect to k, then we have the integral from 0 to infinity of x to the k times log k. Terribly sorry about that. It's actually log x times e to the minus x squared dx. So that means if I differentiate k number of times, that's when I get the integral from 0 to infinity of x to the k times log to the k of x times e to the minus x squared dx. Okay, cool. So how exactly is this integral related to the gamma function? Well, we can uncover that relatively easily. Let me just take this integral down here. We have I of k defined as integral 0 to infinity x to the k e to the minus x squared dx. So we'll just let x squared here equal to u, which implies that dx equals 1 over 2 root u du. So I of k is now the integral from 0 to infinity still. We do have a factor of 1/2 outside though. Then we have u to the 1/2 times k times e to the minus u times u to the negative 1/2 du. I'll multiply out the u terms to get 1/2 times the integral from 0 to infinity. U to the 1/2 or k over 2 minus 1/2 times e to the minus u. And k over 2 minus 1/2 actually equals k over 2 plus 1/2 minus 1. And now we recognize this as the gamma function, specifically the gamma function evaluated at 1 over 2 times k plus 1/2. Okay, cool. So that's I of k. But now if I differentiate this k number of times, we have the kth derivative equal to 1/2 times, on differentiating, we have 1 over 2 k times. Then we have the kth derivative of the gamma function, which of course are polygamma functions, but I'm just going to write it in this way because it looks pretty damn cool, of k over 2 plus 1/2. So I'll just multiply all these factors up front to write this as 1 over 2 to the k plus 1. I'll move this around. So that's the result of our target integral, or the derivative of our target integral. Well, that was our target integral, to be very honest, for I sub k anyway. So all of this implies, terribly sorry about that, that your actual target integral now, that is the sum over, terribly sorry about that, the sum over k of -1 to the k over k factorial times 1 over 2 to the k plus 1, kth derivative of the gamma function, or gamma order k derivative, however you say this thing, of gamma k over 2, no wait, it's the kth order derivative of the gamma function at k over 2 plus 1/2. Again, math, I always say this, math is a lot easier than talking. Can we clean this up slightly? Well, k factorial is gamma of k plus 1. We could write this as, let's see, we could let k plus 1 equal n. So now we have I being the sum over the positive integers n of -1 to the n minus 1 over, we now have gamma n, which is dope, I guess, times 1/2, or 1 over 2 to the n, that is, times gamma order k derivative of n over 2. And oh wait, now it's the n minus 1th order derivative, and that does include the gamma function itself, at n over 2. Okay, cool. Does this thing converge? Good news is yes. Does it have a really cool closed form? Well, no, I believe this is the best we can do, unless one of you, the subscriber base, actually does come up with a really cool closed form for this absolutely insane looking infinite series. But to be honest, not every cool integral is going to have a closed form, which is why I wanted to discuss this, because the idea of an integral involving that Bernoulli integrand and the famous Gaussian does seem very enticing. And the solution development is quite interesting, and the final result, even though it's in the form of an infinite series, I understand that many of you are not going to be satisfied with this, but for me, the result is still aesthetically pleasing. It just looks absolutely insane with the derivatives of the gamma function and the gamma function itself. I think this is still extremely cool. Let me know your thoughts in the comment section on whether or not you actually like results like these, and I hope you enjoyed the video. Be sure to like and subscribe. Do drop me a follow on Instagram as well. Thank you. See you next time.